In our next video here, we're again going to use the graphs of the different functions that we have here, and we're just going to use it to talk about where a function is continuous rather than looking at specific x values that are already picked out for us. So for these types of functions, really the thing that we need to be on the lookout for, we need to be on the lookout for any holes in our graphs, any jumps that we might see, and any vertical asymptotes. Those are the three things that we should be looking out for. Remember, we can always fall back on the definition of continuity on an interval, which says as long as you can draw the graph without picking up your pencil from your paper, it's continuous there. So we're going to use that idea in these examples. So first up, we've got y equals x squared minus 1 over x minus 1. Now, if you were to graph this function, depending on what program you're using, you might not see this hole right here, but this graph actually does have a hole here at x equals 1. If I were to sketch the graph of this function or trace this graph, right? If I were to draw this graph, I don't need to pick up my pencil anywhere except for at that hole. So as soon as I get to that hole, I've got to stop, pick up my pencil, but then after that I can continue tracing, I can keep going. It looks like it's continuous everywhere. So there's a few different ways we can talk about the continuity of this particular function here. We could say it's continuous. Let me write a few different ways. We might say it is continuous for all x values except x equals 1, because that is our discontinuity. So we might say, hey, it's continuous everywhere except for this 1 point or this 2 points or however many discontinuities that we have here. So in this case, we've just got that 1 point. So we could say it like this. However, I'm really going to encourage you to talk about these types of problems using interval notation. So if I were to talk about where this function is continuous, this function is continuous everywhere on the left-hand side of that hole. So I'm going to hold off on that, and I'm going to say, okay, this is continuous on. And so on that left side of the hole, on the part of the graph that I've highlighted right here, when we talk about continuity, we're always talking about it in terms of x values. So if I wanted to give an interval to describe this highlighted section of my graph, well, I want to start with the leftmost x value, but this arrow pointing over here means it's going to keep going to the left forever and ever and ever. So I can't just pick a finite number. I would have to say, well, for that particular part, I'd have to say the left endpoint would be negative infinity. So it's continuous everywhere from x equals negative infinity, or all the way from x equals negative infinity until we get to our hole right here. So stopping at x equals 1. So that's going to be our right endpoint. So we're going to say it's continuous on negative infinity to 1. And now we need to make a decision. Do I want to use parentheses around 1, or do I want to use a bracket around 1? When we use parentheses, if I were to use parentheses around an endpoint, that means that that number is not included in our interval. If you use a bracket, that means that number is included in your interval. So what I want to ask myself is, when we're talking about continuity, we're trying to determine where this function is continuous. Is our function continuous here at x equals 1? Well, no, it's got a hole right there at x equals 1. So that means that we want to use parentheses around 1. But that's only part of where it's continuous. It's actually only half of it. I still need to talk about the right-hand side as well. So it's continuous everywhere to the right of that hole as well. So if I wanted to give a left endpoint, well, it's starting right here at 1. So again, I'm going to use parentheses around 1 because it is not continuous at 1. If I used a bracket around 1, I'd be saying it is continuous at 1, but in this problem it's not. And then I want to say for my right endpoint, again, this arrow pointing to the right means it's going to the right forever, so we're going to approach positive infinity. Around negative infinity and positive infinity, since those are not real numbers, we can't contain them in our intervals. That means we're always going to use parentheses for negative infinity and positive infinity. In between them, there's a few different ways. I don't recall what notation our textbook uses. You can use a U, and that stands for union if you're talking about set notation. Or if you just put a comma in between, that would be fine too. I kind of like to use the U for union, but either way is fine with me. So this is how I would really encourage you to write your answers when we're talking about continuity, because we're going to be using this interval notation throughout this course. We're going to see it pop up again and again and again, and I want to make sure we have a good understanding of it before we get into more complex ideas. Let's look at a couple more graphs. Next up, I've got f of x equals the square root of x. So just to start thinking about where this function is continuous, remember we said our function is continuous as long as you can draw its graph without picking up your pencil from the paper. So if I wanted to trace this function, first of all, it doesn't exist over here on the left-hand side of the y-axis. So it's not continuous there if the function does not exist. We said having the function exist, that was the second part of our definition of continuity at a point. So it's actually not going to be continuous over there. But as soon as I get to 0, okay, it's continuous at that point. And then if I trace my graph, it looks like I'm not going to have any holes or asymptotes. I could just keep going in that direction forever and ever and ever. So if I wanted to talk about where this function is continuous, it is continuous on starting at 0. And then we said, well, just if it keeps going to the right forever and ever and ever, we would say it's continuous from 0 to positive infinity. Now, positive infinity always has parentheses around it. For 0, there's a few different arguments that can be made based on what definition of continuity that you're looking at. Here, I would say that this function is continuous right here at x equals 0 because the function does exist right there at x equals 0. So I would say it is continuous there, which means I would use a bracket to enclose that endpoint. So I would say 0 to infinity, 0 is included, infinity is of course not. So here is my interval where this function is continuous. Lastly, part C, here I've got y equals the cubed root of x. So if I look at this function, okay, if I were to sketch the graph of this function, start over here on the left-hand side. First of all, if I wanted to go even more to the left, I could. I'm just running out of room there. But if I were to trace this function, it doesn't appear that there's any place where I would have to pick up my pencil from the paper. There's no holes, there's no asymptotes, there's no jumps. So if I wanted to talk about this, I could say, well, if there's no discontinuities, that means it must be continuous everywhere. But I want to be able to talk about this using interval notation as well. So I would say, okay, well, this is continuous on, and I want to write an interval for this highlighted portion of my graph right here. So the left endpoint, well, just keeps going to the left forever. So my left endpoint would have to be negative infinity. And then we said there's no place where it stops being continuous, right? There's no point where I need to pick up my pencil from the paper. It keeps on going to the right forever and ever. So that means that my right endpoint would have to be positive infinity. So if we say that a function is continuous everywhere, another way to describe that is to say that a function is continuous from negative infinity to positive infinity.